Chapter 12, Problem 14. In Chapter 12, Problem 14, a bowling ball is thrown onto a lane, and sliding friction starts slowing the bowling ball down. We can use F net equals ma to find the acceleration. The equation for sliding friction force is Fk equals mu k mg, where mg is the normal force in this case. So notice, it's an easy thing to solve for the acceleration of the bowling ball. In this case, the acceleration will be negative because the friction force is going to the left since the bowling ball is sliding to the right. Once we know the acceleration, we can use page 21 to find an expression for the velocity as a function of time. What this shows is that the bowling ball starts out with an initial velocity, v naught, and then it gradually slows down. At the same time the sliding friction slows down the bowling ball's linear speed, it also provides a torque that increases the bowling ball's angular speed. So during the sliding phase, the linear speed slows down, but the angular speed increases. This happens until v equals omega r and smooth rolling occurs. Since we already have an expression for v, namely v equals v naught plus at, all we need is an expression for angular speed, omega, in order to set v equals omega r and solve for t. The likely expression for omega is omega equals omega naught plus alpha t, and in our case omega naught is 0 since we're given that the bowling ball starts with 0 angular speed. In order to find alpha, we have to use torque equals I alpha. One thing I should point out is that the sign of the torque is going to be positive. The reason why it has to be positive is as the ball moves to the right, if it's rolling, it's got to be spinning in the clockwise direction. Therefore, since I've assigned right as the positive linear direction, I must have clockwise as the positive rotational direction. Now, the frictional torque makes the bowling ball accelerate in the clockwise direction, so the frictional torque will be positive and the angular acceleration will also be positive. So starting with torque net equals I alpha, the only torque on the bowling ball comes from the friction force, so it's radius times force times sine of 90 degrees. Once again, friction force is mu k times the normal force, or in this case mu k mg, which is the normal force of the bowling ball on a horizontal surface. So what you should do is solve all those equations for alpha and plug that alpha in omega equals omega naught plus alpha t. In order to find the time it takes for smooth rolling to occur, we're going to plug in our expression for v into this side of the equation. And then we'll plug in our expression for omega into this side of the equation. With omega naught equals 0 and alpha you find from the torque equation. And so therefore you can solve for t. Now interestingly, once smooth rolling occurs, the bowling ball no longer decelerates because sliding friction no longer acts on the bowling ball. In fact, static friction doesn't even act on the bowling ball because it is spinning at exactly the right angular velocity that matches its linear velocity. So it's just moving horizontally with constant speed. So who knew there was so much physics involved with throwing a bowling ball onto a bowling ball lane?